Well, good morning, good afternoon, everybody. Welcome in across the continent. We've got students from like Newfoundland to California today, so it's a really wide range of classes, and a big thank you to all of you for joining us as we continue to celebrate and showcase just the coolest scientists and explorers on planet Earth. If you're joining us today, it's really exciting for a couple reasons. Number one, this is February. This is our entire month solely dedicated to the most awesome women in STEM on planet Earth. We've got 50 broadcasts this month with everything from Egyptologists to paleontologists, Arctic botanists, and more. It's just been a wild ride, and everything is on our YouTube channel. So you can check out like all the programs. In fact, you should check out all the programs right there, right after this broadcast is done. Secondly, we are bringing back one of the coolest people we had last year, which is Dr. Munazza Alam. She is at the Space Telescope Science Institute. She's had an amazing early career in science and astronomy. She's a National Geographic explorer and more. And today she's going to talk to us a little bit about her amazing journey and some of her work hunting exoplanets, which is surely one of the coolest jobs on planet Earth and beyond, literally. So it's a very exciting opportunity to have her back. Before I bring her in, I want to highlight we do have a Kahoot today. So between the talk and the Q&A, if you want to play along with a little 4-question quiz, have some fun, test your understanding, win some bragging rights. You can pull up that game pin and do just that. But without further ado, I'm going to zip my lip. It's not about me. Even though I've got a cool moon globe behind me, I'm going to turn you over to Dr. Alam to blow your minds. And thank you so much for joining us again. And welcome back to the broadcast.
All right. Well, thank you so much for having me. So as Jesse mentioned, my name is Munazza Alam, and I'm an astronomer. And I specifically use observations from space-based and ground-based telescopes to study the atmospheres of exoplanets, or planets beyond the solar system. And today I'm really excited to share with you my journey on this path through school and to exploring space today. So for me, this all started when I was in high school and I decided to study physics. When I was younger, I always was very interested in how things work, how the natural world works, how machines work, how we can understand what is going on in the world around us. And I found that the answers to a lot of these questions that I had can be answered by studying the subject of physics. And I took my first physics class in high school. I had an amazing teacher. Her name is Dr. Jensen, and she was an absolute inspiration to me. The class itself was very challenging. It was really hard, but she was very encouraging and encouraged me to keep trying to understand topics that were difficult for me to understand until I finally could get it. And she was also the first woman I knew who had worked in physics, and she made me feel that I could do the same. So after high school, I went to college and I found my passion for astronomy in college. So I was studying physics, but I met a professor who was working as an astronomer, and she invited me to join her research group. So this is actually a picture of my college. I went to college in New York City. It's called Hunter College. And it's kind of funny when I think about it that I actually started doing astronomy in New York, because when we think about New York, the night sky looks something like this. There's so many bright lights of the city from all of the buildings and the bridges that it's really hard to see the stars, because the stars are outshined by the lights of the city itself. But I really fell into astronomy while I was in college in New York, because I was working with a professor at the American Museum of Natural History, which is shown here. The American Museum of Natural History is known for its famous planetarium, which is shown here. And I was able to join a research group that was asking some questions, some research questions, and tackling those hard astronomy questions. And so when I talk about research, what I mean is asking questions to better understand the world around us and trying to find creative ways to answer those questions. But the thing about research is that the questions that we usually ask when doing research are questions that nobody in the world knows the answer to. And so in many ways, and this is probably my favorite reason for doing research, working on research is like working on a jigsaw puzzle. If you've ever worked on a puzzle, maybe of 500 pieces or 1,000 pieces, you may have looked at the box of what the puzzle is supposed to look like to get a sense of where to put the pieces together. So research is just like that. We need to work on a little piece and start connecting it to another piece of the puzzle. But there's one big catch, and that catch is that we don't have the box. So we don't know how the puzzle pieces fit together, and we don't know what the final picture is supposed to look like. But that's also why it's really, really important when doing research to collaborate with others around you who also do research, who can better help you to answer these questions. Now, I mentioned that I started doing research when I was in college, and I wanted to talk a little bit about my first research experiences because these first research experiences are the reasons why I have become an astronomer today. So I started working on the smallest stars and trying to better understand what those stars are like. And as part of this research experience, I had the good fortune to travel to observatories in faraway places that I had never been to before, like Arizona, Hawaii, and Chile. So these are some pictures from my first research experiences. In particular, I had to travel to these places to go to the observatories and use the telescopes, which are shown here, in order to collect data for my research. And if you look closely in these pictures from my trips, you can even find me in some of them. Now, I had never been to any of these places before where these observatories were located, and they're very unique and special locations. So observatories with telescopes are actually built in really, really unique places on Earth that make it extra good for us to have access to the night sky and collect really, really good observations of stars and planets and galaxies. And some of the factors that we look at when thinking about where it is a good location to build an observatory have to do with the fact that we want the location of an observatory where we have our telescopes to be remote. We want it to be far away from the city lights. Like I showed the picture of New York City earlier, you can't really see the stars when you have all these bright city lights, but when you go far away from the cities, out into remote places, the skies are very dark, which give us a really clear view of the stars. We also want to place observatories in locations that are very high up, so usually at higher altitudes or on top of mountains, because that's where the atmosphere of the Earth is thinner, so we can get a better view of the stars and planets and whatever we're observing. And lastly, we want the locations of our observatories to be dry. And that's because we want to make sure that we aren't having any weather like rain or storms that are going to interfere with the telescopes and the machinery that we have inside of the telescopes. And so it's best to have observatories in places where we have little rainfall, so typically like deserts, for example. So these are some of the aspects of the places where these observatories are. And now when I travel to the observatories to get data for my research, I use telescopes like this. And these telescopes are a little different from the types of telescopes that you might have used before, say, in your backyard. The first big difference between these telescopes is the fact that the telescopes at observatories are huge. They're about the size of a school bus. And just to give you a sense of the size of these telescopes, here's me standing in front of a telescope in Chile, and you can see just how massive it is. To give you another sense of how big these telescopes are, here is a picture of the inside of a telescope. This structure over here is the mirror of the telescope. It's about 10 meters in diameter. This is the Keck telescope in Hawaii. And we actually had the mirror pointing at us. And so I was with some of my colleagues and we took a selfie in this mirror. But you can see that this mirror is very large and we look so tiny in comparison. And also, while we are at these observatories, we are not looking through the eyepiece of the telescope the way that you might if you set up a telescope in your backyard and we're looking at the moon or Jupiter. Instead, what we do when we operate these really big telescopes at observatories is we sit in what's called the telescope control room, which looks something like this. So it's got many, many different computers, and each of them control a different aspect of the telescope itself. Some of the computers have controls that we can use to tell the telescope where to point. Other telescopes have controls that allow us to tell the telescope how long it needs to point. And kind of moving between these computers, we can make sure that we're observing as we want to smoothly throughout the night. So it was my first experiences traveling to observatories and taking my own data for my research project that really solidified for me that I wanted to become an astronomer, because as a kid from New York City, I was so used to night skies that were very bright from city lights. But when I traveled to observatories, it was the first time that I saw a night sky that looked like this, with a night sky illuminated by hundreds of thousands of stars. And it was just an absolute breathtaking experience for me. And I knew that I wanted to continue being an astronomer long term. So I continued on in schooling to become an astronomer. And today I do research in astronomy. And in particular, I study exoplanets, or planets outside of the solar system, using observations from the Hubble and James Webb Space Telescopes. So here's a picture of the Hubble Space Telescope on the left, and here's a picture of the James Webb Space Telescope on the right. And these telescopes are different from the telescopes that I was talking about earlier, because these are telescopes that are in space. So they are big, precise, and give us amazing, amazing data. And in particular, I use both Hubble and Webb in order to study the atmospheres of exoplanets. So our planet Earth has an atmosphere, and in our atmosphere, we have clouds that are water clouds. So when it rains water. We have kind of weather, and sometimes it's summer, sometimes it's winter, sometimes we have winds. And I'm interested in what those weather patterns and climate is like on planets beyond the solar system. And the way that I do this is by studying planets when they transit or pass in front of their stars from our line of sight here on Earth. And I have a little cartoon that illustrates this. So in this cartoon at the top, the star is the yellow circle, the planet is the black disk, and then the little blue ring around the planet is its atmosphere. So if we observe the planet when it passes in front of its star, and we measure the brightness of the star over time, we'll see that we see a dip in the brightness of the star. That is actually due to the planet casting a shadow on the star. And so when we measure the brightness over time, we'll get this dip in the star's brightness, and the size of the dip is roughly proportional to the size of the planet. And if you wanted to see what this cartoon effect looks like with real data, here's an example of real data of a planet transiting or passing in front of its star, as measured from the James Webb Space Telescope. So we're measuring the brightness of the star over time, and the brightness of the star is shown by these yellow dots. And we can see that when the planet is in front of the star, we get this dip due to the starlight blocked by the planet. We can take this effect one step further and measure the atmospheres of what these planets is like by measuring these dips in starlight at different colors of light. And the reason why we can do this is depending on what color of light we look at, whether it's a blue or a green color of light, we see that the size of this dip that the planet will cause when it's in front of the star is slightly different. And so we can use those slight differences in the size of the planet at different colors of light in order to figure out what is in the atmosphere of the planet. If you don't believe me, we can look at real data to see what this looks like. So on the top, I'm showing similar curves of the brightness of a star over time, where the dip is where starlight blocked by the planet and its atmosphere. And the different wavelength or color of light that we see here is represented by the different colors. So there's a blue color, a green color, and a red color that we're looking at. And if we zoom in on the bottom of this curve and look at it, we actually see that at the red color of light, the planet's atmosphere blocks less light, but at the green color of light, the planet's atmosphere actually blocks more light due to the absorption of carbon dioxide gas in the atmosphere of this planet. So we can put all of this information together. If we measure the size of the planet at different colors of light and then put that on a graph, we'll start to see all of these bumps and wiggles. And those bumps and wiggles correspond to the fingerprints of all of the different gases and molecules that are in the atmosphere of the planet. Now, if you saw earlier, the difference between the green dots and the red dots in the transit data that we were looking at is really small. And that's something important to realize when we're working on this. The signals that we're looking for the atmospheres of these planets are really, really, really tiny. But we have these great observatories, these great telescopes like Hubble and James Webb that can allow us to find those tiny signals and understand what those tiny signals are telling us about the atmospheres of these planets. And we've been able to use this technique to study the atmospheres of many different planets. And what we're finding out is that a lot of the exoplanets out there are very different from any of the planets in our own solar system. I want to highlight one of my favorite exoplanets, which is called HAT P7b. This is a planet that is similar to Jupiter in our solar system, meaning that it's puffy and it has a lot of gases, but it's really, really close to its host star. So close, actually, that a year on this planet is just a few days long. And that makes it really, really hot. And so in this unique, interesting, exotic planet, there are clouds in its atmosphere, but those clouds are actually made of a mineral called corundum. And that mineral is the mineral that makes up rubies and sapphires. And so when those clouds rain, the raindrops are actually made of rubies. And I think that this is really neat because it tells us so much about the exotic, unique planets that exist within our very own Milky Way galaxy. And what's even more interesting, at least to me, is that this sounds like a science fiction world, but it's not. It's a real planet that exists within our very own Milky Way galaxy. And so whenever I think about the work that I do and exploration of planets, I think that there's so much more that we can think about and discover and explore. And there's so many questions that we can ask that we don't yet know the answers to. And so there's so much room for more research to come. And so with that, I hope that you have been excited to learn a bit about exoplanets today, and I'm excited to hear your questions.
What a cool career story and what amazing work. Every time we get to feature the James Webb Space Telescope and some of its discoveries is just mind-blowing. Like, this is, students, you guys have been around for the launch of this. Like, if you're in grade 4 now, I think this launched a few years ago, you'd have been in grade 1. And the discoveries it's already made have upended astronomy. Like, it's really, really exciting for someone who grew up waiting for the James Webb Space Telescope and working with people that were getting excited about it to see it go into orbit and beyond and just make all these incredible things, discoveries in the universe around us. So Munazza, thank you so much for that. What we're going to do first is dive into a little Kahoot to test some understanding on some questions that we covered elements of. Some of them we did not cover elements of. So we're going to play a little 4-question quiz together, and then we are going to head to Dr. Kizier's class for our first question in Milton, Louisiana. So we've got Louisiana kids, Illinois kids, BC, California, Ontario, all sorts of folks. But if you want to pull up our game pin with our Kahoot, and if you're new to Kahoot, the faster you answer, the more points you get. And what you win is Munazza and I's everlasting respect, which is pretty great. So no pressure at all. Feel free to play in with that. We'll give you guys a few seconds to join in. I want to note, too, if you want a great follow-up to today's broadcast on our YouTube channel, my colleague Joe just wrapped up with astronaut Jessica Meyer as sort of the in-space perspective on space exploration. And we've got a bevy of questions already. So we're going to start off. And Munazza, if you want to give us little hints as we go along in this, there's about 20 seconds for each question. Feel free to guide us in the right direction. All right. All right, 3, 2, 1, and here we go. And classes, I will come to you live for questions. You don't need to share them in the chat because we're all good for tech. How many exoplanets, so planets in other solar systems, have we found so far? We featured some of your favorite ones, but is it 5, 50, 500, or over 5,000 exoplanets? What do we think? Any hints?
Hints that I'll give you is that we think that every star that we look up at the night sky might host at least one planet.
Ooh, this one really threw people off. So over 5,000 is our correct answer. We're at what? We must be at the latest number I saw was 5,200, but I know that we've probably seen more than that. And
I think we're closer to 6,000 now.
Yeah, there you go. And like that's we're barely started scratching the surface of this. Like literally, I would say when I was 25, we were like, maybe there's some exoplanets out there, and now we found over 6,000. So Creative Hamster takes our lead. There's a lot out there. True or false? We talked about this explicitly. The transit method helps us find planets because they block out some of the star's light. So I think, this is what's great about this is that it's neat science, but it's really easy to understand. I've got a light above me. If I wave my hand in front of it, it blocks some of the light. And you can literally see that. You can do this with a lamp in your classroom. So we all instinctually understand this, which is kind of neat. And I think our audience, overwhelmingly, 90% got it right. So yes.
Very nice.
You highlighted too, which we addressed a little bit in the next question, but like it's so tiny. Like imagine looking at something that is as far away as some of these other planets are and being able to understand perhaps, is per this question, what its atmosphere is made of or how big it is. I mean, these aren't just around the corner. Mars is like our next door neighbor and is like an 8-month vessel journey away. These planets that we're looking at are how far away? Like tell us a little more.
They're several light years away. So a light year is the distance that light travels in 1 year, and light travels very, very, very fast. So if we wanted to get to some of these planets, it would take us decades. You would be old by the time we got to
old. So old. My favorite way of putting it is this: our fastest spacecraft we've ever built ever that like got to Pluto in a few years. If we tried to send it to the next star, I think it would take 18,000 years. Like it's incredibly, insanely far away. And that's just the next closest one. And we can look at those and figure out what their atmospheres are made of, which is like black magic. It's so cool. And I love it. All right.
And the other thing that I want to say is we can't actually see these planets.
Yes. We just infer from all this data that you're talking about, which is so neat. So Purple Camel's got our lead. We'll talk more about that in a second. What is this a picture of? Is it fake and AI generated? Is it some stars from a dark place? Like you go out and you see some stars like we showed in Chile? Is it just a painting? Or perhaps fitting with my theme in Cahoots, is it thousands of galaxies in a tiny patch of night sky? So most of you got it this right. Can you tell us what that image is? Because it's my favorite image in all of science. It's so great.
So this image is a picture of what's called the JWST deep field. So this is a picture of a portion of the sky that was taken with JWST. But what I think is the most interesting and cool part about this picture is that it's actually a really, really small fraction of the sky. And the way that I like to think about it is roughly equivalent to if you took a single grain of sand, held it between your fingers at arm's distance, and you looked. That is the portion of the sky that image is showing. So it's a really, really small part of the sky, but we can see so much detail, so many galaxies and stars, and just we can see that space is filled with these interesting things that we don't yet know all the answers to.
Every time I think about it and you really take it in, it gives me chills. Like it's really to think that every patch of night sky that's the size of a grain of sand has thousands of galaxies that we can see with these tools, and that every patch of sky is like that. Like we're talking billions and billions and billions of galaxies, each of which have as many stars as the Milky Way. Like all the stars you've ever seen if you've been to like a park or an amazing place like Chile. It's unbelievable. And as you said, we think that most, if not all, will have planets, and some have multiple planets, like our solar system does, which is crazy. Infinite worlds out there. So I'm going to stop being way too excited, and I'm going to turn us over to our Louisiana crew for our first question, and then Avoca West, you guys are going to be next. But Dr. Kizier's class, if you guys want to flick on your mic and come on in, I can bring you into the broadcast. And if not, we did share a great one in the chat, so I can always come to you in a second. So I'll say, what kind of data do you wish you could extract from exoplanets? If you could find, if there's a dream thing you could find out with our cutting edge tools, what is it?
So one type of data that I think that we just need to get a little bit more handle on the types of planets that we can find these on, and also have a little bit more precision and more powerful instruments, is data that are or results that are what we call biosignatures, so signatures of the fingerprints of life. I think that is really the next step in what we're trying to understand about exoplanets. We now have found like almost 6,000 exoplanets, but we only know of one planet that hosts life, which is our planet here on Earth. And so one natural question that comes from studying all of these different planets is, well, do other planets host life? And the only way that we can really answer that question is if we start looking for life. But that's a really, really hard thing to do. There's so many planets out there that are similar to the Earth, but for many reasons, might not be able to host life. And there are also planets that could be the twin of Earth, have similar oceans on them, but still could not necessarily have life on them. So I think it would be really cool to find these biosignatures, these fingerprints of life. But then once we do find them, we would have to make sure that we rule out all of the reasons that we could see those biosignatures that are not life before we infer that potentially there could be some life there.
So your thing that you're trying to find is the greatest question in the history of mankind, which is, are we alone in the universe? Which is very exciting. So because we got a question that's very linked to this. Our Canada crew in Ontario, they are having a few tech difficulties on StreamYard, but on YouTube, could the planet you highlighted possibly have life? Like, is there something specific we're looking for? What is one of those signatures of life that you could maybe share with us that we'd be trying to find?
Yes, so I would say HAT P7b could not host life. It is way too hot, and that's just I definitely wouldn't want to live there. But some of these fingerprints of life that we think about are like oxygen, carbon dioxide, methane, ammonia, the types of gases that we see in the atmosphere of Earth. And if we took a measurement of the atmosphere of Earth, that would be smoking gun evidence that life exists on Earth.
And I love that you mentioned this, because the idea that we can take satellites and look back on our own planet, and if we didn't know, like if we weren't part of Earth, you could look at the Earth and be like, life, for sure, 100%, absolutely. So we're looking for things that are like us. And so within our own solar system, we've talked about the Europa mission, Enceladus, Titan, Mars missions looking for life. So it's just, for kids, I always like to stress, and you can attest to this, it is the golden age of space exploration. Like if you're keen on anything, it's the best time to ever be interested in this ever. Like it's so cool.
We have the best technology and spacecraft and knowledge today that we've ever had, like in the history of humanity. So now is definitely the time to start looking and to be thinking big.
Well, we've certainly got a lot of curious kids, so I'm going to head to our Glenview, Illinois class for a second. Division 2, and Miss Becker, I'm coming to you too, I promise. We've got tons of time for Q&A today, so come on in Illinois and take us away. Hey.
So is it like 50-50 that aliens are like real, and if they like would they be like dangerous kind of?
Great question.
Yeah, so we don't have a good sense of if it's 50-50 or any other type of probability just yet. But just thinking from the fact that there's so many planets out there, it would be very unusual if Earth was the only planet that had life. But one thing that is really important to start thinking about is the life that we're looking for too similar to Earth? And is it possible that, given how different these planets are from Earth or the other planets in the solar system, is it possible that we need to start thinking outside of the box in terms of what types of life could exist and what we should be looking for. Right now, I think a lot of our focus has been looking for intelligent life like us. And also a lot of our focus has been looking for carbon-based life forms, again, like us. But maybe different planets can give rise to, with different conditions and different temperatures and different histories, can give rise to different types of life.
Cool. On Earth, we feature a lot of speakers that go to the most remote and extreme places on this planet, and really wherever we look, whether it's acid baths, middle of Antarctica, like you name it, we find life. So it is remarkable how resilient and amazing life can be, and the more we're learning that, the more we're exploring new places to look for it. I will say, to your question and to your note about how many planets there are, literally every single astronomer, astronaut, person involved in space we've ever featured on the broadcast has mentioned that they are in team, yes, of course, there's life elsewhere in the universe. We've never had anyone who's been like, I don't think so, because there's just so many worlds, and it seems so unlikely that it would just be us. So great question, guys. Division 2, Duncan, BC, we're heading to you. Come on in the West Coast and take us away. Hey, guys, Mr. Horseman's class, welcome in. Hi.
Mr. Horseman. Sorry, just 1 minute, please.
All good. I'll come back to you guys in a second. Announcement while we do the question. Miss Becker's class, San Diego, I'll come to you guys. Come on in. Hey. Perfect.
You are.
If you said it rains ruby in the planet Happy 76, if it snows there, will snow be different?
So it definitely wouldn't snow on that planet because it's so hot, like thousands of degrees. So it definitely wouldn't snow at all. But if it could, it would be different as well. It wouldn't be the type of snow that we're used to.
Yeah. Again, the fact that we can even think about this and know this is just unbelievable. And it's all happened in the last like 10, 15 years of my lifetime. So it's really, really exciting science. And I love that you guys are thinking about these questions. Division 2, I think the announcement's done. I'll come back and we'll check in. Hi, guys. Let's see. Oh.
My name is White, and my question is, how do you name planets when they're first found, and why do all the new ones have just letters and numbers, just a mix of them, just that?
So the names of planets are really interesting. So they're named after the name of their star, and then they're given a letter that starting with B for the first planet that we discovered around that star. And if, for example, I talked about HAT P7b, that's the first planet that we discovered and the only planet around that star. But if there was another planet, we would call it HAT P7c, and so on. And so the reasons why these stars and these planets don't have names like the names of the solar system planets is because there's so many. There has been a bit of a movement and kind of discussion about, do we start naming some of the more famous exoplanets? And if so, what would that name be? But there's almost 6,000 exoplanets, and so we would need to come up with 6,000 different names. And the names of the stars themselves also come from surveys of portions of the sky that tell us about that, so that have been used to discover stars. So HAT-P is the Hungarian automated telescope, I believe.
Cool.
And so it's a survey that was looking for stars, and so that's the name of that. There's some planets called WASP, and then have a number, and that's just the wide angle search for planets. So they're not really interesting names, but it's kind of the way that we keep track of all of the thousands and thousands of stars that are out there and the thousands of planets that are out there.
We had a really interesting analog to this exact question at the beginning of the month with the bug zoo in Missoula. So if someone asked, do you name all the insects? And they're like, we got like 50,000 of this thing. Like, we don't name them all because we couldn't even do it. Whereas if you have something like a gorilla, it's easy. Oh, there's one over there. Oh, there's Jupiter. Makes it a little more readily available. Great question, guys. All right. I'm taking a YouTube one. I love when we get this. We never used to get questions like this, so I like to feature them when we get them. Our Miss Wallace class wants to know, are astronomers in general well compensated, or do you just do it for personal interest mostly?
I think that we're not as well compensated as other jobs, but I still love it anyway.
We only ever used to get them from grade 11s, and the age range of classes asking about money in various science jobs has gone way up in our career. So thank you for that, guys. Dr. Kizier's class, if you guys want to share in the chat, I'm sorry it's being a little iffy with your connection today, but we're going to head back to Avoca West. Come on in Illinois and take us away for a second question. Hey, guys.
Have you found any other life forms like plants or anything?
Ooh, yes.
No, we found no other life forms, not even plants. Like, yeah, forget about little people, little green people. We haven't found any plants. We haven't found any like microbes or bacteria. So it's still, that's also a possibility. And I think when we get this question, do we think that life exists? One of the reasons why we almost always when especially astronomers are asked this question, why we typically say maybe yes, is because there's so many different types of life forms that, for example, formed early on in Earth's history before humans came to be, and that's definitely what we're thinking about.
Yep. I like highlighting too for our audience, like on the microbe note, like in the whole history of life on Earth, life has been around for 4 billion years and animals appear about 700 million years ago. So if aliens visited the Earth for most of the Earth's history, they'd have been like, oh, it's a watery soup full of, bacteria. That's it. And they would have gone away and been like, oh, there's nothing intelligent here. And so it's really, you have to change how you think about life in the universe. Let's put it this way. If we ever did find a microbe on another world, Mars or the moon or anything, it would be international news for like weeks and months on end. It would be the biggest discovery in the history of science if we ever make that discovery. So I love that question, guys. And thanks for skipping recess in Glenview to hang out with us today, by the way, too.
Thank you.
Division 2, come on in and take us away in Duncan. And then Miss Becker will wrap up with you guys in just a second. Hey, guys.
Hi, my name is Alex, and my question is, how does Hat P7b have ruby rain?
Ooh.
Yeah, so that's a really, really good question. So the reason why it has ruby rain as opposed to water rain like we have on Earth is because this planet has had its own unique way that it formed from different materials that the Earth formed out of, which means that it had different materials available to make its atmosphere. And also, it has a really unique chemistry going on inside of that atmosphere, which already has a different composition or makeup than the Earth's atmosphere. And the chemistry and the physics is so different because this planet is much, much, much bigger than Earth, for example, and also much, much, much hotter. As I said earlier, thousands of degrees. And so at these really kind of extreme temperatures and at these extreme sizes or pressures, we get really exotic physics going on. And that is also due to the different materials that the planet formed from.
Yeah. I love that we've had the name of your planet been referenced like 8 times in questions. That's the most that anyone's ever talked about something that isn't in our own solar system ever in our history. So way to go for highlighting that. We're going to take one from our Miss Becker crew, and then we'll do 2 quick ones from Avoca West because you guys did skip recess, and then we'll wrap up after that. I love your enthusiasm. California, sunny California, come on back in. Hey, unmute and you're good to go. Hey, guys.
Which planet, if we had to abandon Earth, which planet would we most likely go to?
Ooh.
Maybe if we have to, I hope that we don't have to abandon Earth. Maybe Mars because it's our neighbor. But I would say that rather than thinking about abandoning Earth, we should think about taking good care of Earth, making sure we're being good to the environment, making sure that we are being good to our planet, which has been our home and so graciously given us a lovely place to be where we can walk outside in t-shirts when it's summertime.
We had a Mars expert on the other day, and she highlighted the fact that even if Earth went to absolute, was as worst as it could be, like the day after the meteorite wiped out the dinosaurs, it would still be easier to live on than Mars. Like Mars is insanely challenging, and we'd have to get people from Earth to Mars. And so it would be way better to just build a dome here if things went to really terrible. So keep Earth going, and there's our good message du jour. All right. Avoca West, we're going to take 2 quick ones from you, and then we'll wrap up and say farewell, everyone. Come on in Illinois, and you can share both questions at the same time if you want. Hey, come on in.
On other planets, have you found any planets that rain other minerals other than rubies?
Great question.
Yeah.
Oh, go ahead. You can answer that one, and we'll take the second one in a
I
second.
was going to say my second favorite planet is a planet that when it rains molten glass, so melted glass. And that is also due to the fact that its own unique materials that formed that planet, as well as its own unique chemistry and physics and history as it evolved over time, has led to its clouds being made of a material that would rain molten glass.
So cool. It must rock to be you. All right, one more question. Come on in, ladies. Hi.
Do you know how big the rubies are?
I do not, and unfortunately I don't know, because if I would, I'd be interested in getting an upside down umbrella to catch them.
Yeah. So kids, they can be as big as you want them to be in your minds. That's the perfect takeaway. I want to highlight for everyone, if you want to check out this program, share it with friends and family, watch it again. It's on our YouTube channel. Munazza has an amazing website. You can learn more about her incredible work here, and we'll share that with all the classes at the end of the broadcast as well. But before we wrap up and bring in all you students to say a big thank you and farewell, is there any last message you want to leave our kids with today before we say goodbye?
Yeah, I just wanted to say thank you so much for all of your questions. You have amazing curiosity. Don't stop asking questions and thinking about how the world works, and just keep looking up.
Keep looking up. No better message than that. I hope you all take the chance to go out inside and explore the night sky tonight. And as we do to wrap up every broadcast, I'm going to bring in all our students to say a big thank you and farewell. So Avoca West Division 2, Miss Becker's class, thank you so much. Hey, everyone. Bye, everyone.